Welcome to the Ultimate DBMS Crash Course, your one-stop tour of the fascinating world of database management systems. Whether you're a developer, a student, or just someone curious about how data powers our world, you've landed in the right place. In this course, we're not just memorizing terms, we're breaking down the logic, architecture, and inner workings of databases. By the end, you'll understand not only how to design a solid schema, but how to write powerful queries, normalize like a pro, and keep data secure, efficient, and reliable. Here's a quick roadmap of what we'll cover. DBMS Essentials, DBMS Architecture, the Entity Relationship (ER) model, the Relational model, Functional Dependencies and Attribute Closure, Normalization up to BCNF, Relational Algebra, SQL, including DDL, DML, joins, and subqueries, and finally, transactions, concurrency, and indexing. By the end, you'll be able to design, query, and optimize databases with confidence. So, get your notes ready, and let's build your DBMS foundation, one idea at a time. Let's begin with DBMS basics, the foundation of everything to follow. What is a DBMS? A database management system is software that lets you store, manage, retrieve, and manipulate structured data easily and efficiently. Think of it as a super smart assistant for your data. To see why DBMS matters, let's rewind time a bit. Imagine you own a library with thousands of books. Using traditional files, you might store each record in a separate file. One for books, one for members, and another for history. Now imagine asking, what books has a member borrowed in the last year? You'd have to dig through files, cross-reference manually, and hope there are no duplicates or errors. That's inefficient and risky. But with a DBMS, everything is organized into structured tables, linked by keys. You query exactly what you need. Fast, consistently, and securely. Here's what makes a DBMS superior to file systems. Data integrity. Everything stays consistent. Redundancy control. No unnecessary duplication. Security. You control who can access what. Backup and recovery. Restore lost data easily. Concurrency control. Multiple users, no conflict. Intelligent querying. Ask complex questions and get instant answers. Let's go back to the library example. With a DBMS, you instantly check book availability, see who borrowed what, track overdue fines, all from one interface. Or in banking, it manages millions of daily transactions, updates balances, verifies transfers, and keeps your money secure. From your neighborhood library to international banks, DBMS is the engine behind modern data operations. Now, let's explore the architecture, the structure behind the system. Just like you wouldn't build a skyscraper without a blueprint, DBMS architecture gives us an organized plan for how databases operate. There are three primary models. One-tier architecture. It's everything. User interface and data. Lives on one machine. Think a standalone app saving to a local file. Simple, but not scalable. Two-tier architecture. Split into a client and a server. The client handles the interface, and the server stores data. Perfect for school systems or hospital databases. The three-tier architecture is probably the most common and scalable setup today. It's made up of three layers. The presentation layer, which is the user interface, application layer, the business logic, and the data layer, where the information lives. Here's an example. You use your bank's web app, presentation, which sends requests to the backend system, application, which fetches info from the database, data layer. This model is secure, scalable, and easy to maintain. This is about abstraction, separating what users see from how data is stored. We do this in 3 levels. 1. The external level, what the user sees. 2. Conceptual level, logical structure, entities, relationships, constraints. And 3. Internal level, physical storage on disk. This separation allows independent work across teams. Users don't worry about storage, and developers can optimize without affecting user views. There are 2 golden principles here. 1. Data abstraction. Users only care about what data is, not how it's stored. Like using a search bar without knowing how Google stores results. And 2. Data independence. Schema changes at one level won't impact other levels. Changing your storage format? That's physical independence. Changing table structure without breaking apps? That's logical independence. These 2 make database systems flexible, maintainable, and scalable. Now, we're going to learn one of the most important skills in database design: constructing and interacting with models, or entity relationship models. We cannot design a database without knowing something about the real-world data that it will store. modeling lets us do just this. By dissecting data into entities, attributes, and relationships in a clean and graphical way. But what is an entity? An entity is a real-world object or concept for which information is stored about it. In a university system, typical entities are a student, course, professor, and a department. Each of these has its own properties, or what we call attributes. Attributes are the data fields or qualities of an entity. For a student, some attributes might be student ID, name, date of birth, or email. But all attributes are not alike. Let's talk about some types of attributes. Composite attributes. These are the attributes that are built from smaller pieces. An example, a full name can be broken down into first name, middle name, and last name. Derived attributes. These are the attributes that are extracted from other information. Age can be calculated from date of birth. Derived attributes won't generally get stored. They get computed at the time they're required. Let's talk about the attributes that make it possible or enable us to uniquely determine records. 1. Primary key. The main attribute that uniquely identifies an entity. For student, it may be student ID. 2. Candidate key. All the possible attributes that can be a primary key. One of them is chosen as the primary key out of them. And 3. Foreign key. An attribute in an entity that is a reference to another entity's primary key. These establish relationships between entities. Here's an example. In the enrollment entity, student ID is a foreign key to the student entity, and course ID is a foreign key to the course entity. Relationships. A relationship signifies how entities relate to each other. Here's an example. A student enrolls in courses. A professor teaches courses. A department offers courses. Relationships can even possess attributes, like the enrollment date in a student enrolls course relationship. Now, let's put everything in place. Imagine we're designing a university database. Here's a simple model. 1. Entity is student with attributes like student ID, primary key, name, email, date of birth. 2. Entity is course with attributes like course ID, primary key, title, credits. And 3. Entity is professor with attributes like prof ID, primary key, name, office. Relationships. Student enrolls in course. Professor teaches course. Each relationship might also have constraints. Cardinality, allowing one student to enroll in many courses. Each course can have many students corresponding to many. Participation. For example, every course must be taught by a professor. This indicates total participation of the course entity in the teaches relationship. This diagram helps us think about the structures before writing code or creating tables. In brief, models help map problems in the real world to a database-friendly structure. Learning about entities, attributes, keys, and relationships is the first step towards designing an effective database. In the next lesson, we'll take your model and convert it into a relational model, the table-based structure you'll use in SQL. Now, we'll explore the relational model, the foundation of modern databases. Once you've created an diagram, the next step is to translate it into the relational model, where data is stored in tables. Let's understand the core building blocks. What is a relation? In the relational model, a relation is essentially a table, a collection of data organized into rows and columns. Each line is called a tuple. It is one record. Each column is an attribute. It is a property or field of the data. And each attribute has a domain that indicates the type of data it can hold. For example, in a student table, student_ID is in the integer domain. Name is the string domain. And date of birth is the date domain. This preserves data consistency and keeps emails out of the birthday column. Let's clear up a common misconception in databases: the difference between a schema and an instance. A relational schema defines the structure of a table. Think of it as the blueprint. It includes the table's name, the column names, and their data types. For example, a database of student has student ID, an integer, a name, which is a string, and a date of birth, date. This schema tells us what kind of data the table will hold, but not the actual data itself. A relational instance, on the other hand, is the actual data in the table at the specific moment in time, the rows that currently exist. While the schema stays the same, the instance changes as we insert, update, or delete data. So in simple terms, a schema equals structure, an instance equals content. In the relational model, constraints are rules that keep our data accurate, valid, and meaningful. Let's break down the most important types. Domain constraint. Every attribute must contain values from a specific valid set, its domain. For example, the attribute age must be a non-negative number, not a string like hello or a value like -3. Key constraint. Every table should have a primary key, a unique identifier for each row or tuple. For instance, no two students should have the same student ID. Also, primary keys can never be null. They must always contain a valid value. Entity integer constraint. This builds on the key constraint. It ensures the primary key is never null. Why is this important? Because without a unique non-null ID, we wouldn't be able to reference or locate specific records reliably. In short, these constraints are the foundation for maintaining data integrity in relational databases. Another vital rule in the relational model is the referential integrity constraint. This rule ensures that foreign keys in one table must match existing primary keys in another table. For example, if enrollment.student_ID is a foreign key referencing student.studentID, then you cannot insert an enrollment record for a student who doesn't exist in the student table. If you try to do that, the DBMS will reject it. This prevents orphan records and keeps your data consistent, accurate, and trustworthy. A quick recap on the relational model. Data is stored in logical tables. Tuples, which is rows, attributes, columns, and domains are value types. Define how the data is structured. Schemas define the structure. Instances are the current data. And constraints ensure your data is clean, valid, and meaningfully connected. Now, we're diving into one of the most critical concepts in a relational database: keys. Keys are what gives structure to our tables. They ensure that data can be uniquely identified, accurately related, and reliably retrieved, without confusion or duplication. Let's start with a superkey, which is any combination of attributes that can uniquely identify a row in a table. Let's take an example from a student table. Your attributes: student ID, email, and name. Now, these combinations are all valid superkeys because they uniquely identify each student. Student ID and student ID plus email. Even though student ID alone is enough, combining it with other attributes still makes it a superkey, just a less efficient one. Let's now focus on two essential types of keys that power relationships in relational databases: primary keys and foreign keys. A primary key is the chosen candidate key that will be used to uniquely identify each row in a table. It must be unique for every row, it cannot be null, and there can be only one primary key per table. For example, in our student table, if we chose student ID as the primary key, then email, though also unique, becomes an alternate key, a candidate key that wasn't chosen. A foreign key creates a relationship between two tables by referencing the primary key of another table. For example, in a separate enrollment table, we might have student ID and course ID. Here, student ID is a foreign key that points to the primary key in the student table. This ensures that every enrollment record refers to a real, valid student. The bottom line: primary keys uniquely identify, while foreign keys connect and enforce integrity between related tables. We just saw that superkeys can have extra attributes, as long as they uniquely identify a row. But what if we want the most efficient version of that? That's where candidate keys come in. A candidate key is a minimal superkey. It has no unnecessary attributes. It's the most concise way to uniquely identify a row. Let's go back to our student table with the following attributes: student ID, email, and name. Now consider the possibilities. Student ID is a candidate key, assumed unique and minimal. Email could also be a candidate key if every student has a unique email. Student ID plus email is not a candidate key because it's not minimal. We don't need both identifiers. Here's an important takeaway. A table can have more than one candidate key, and any of them could be chosen as the primary key. Let's walk through a simple example to understand how to find candidate keys. Your table: employee, attributes: employee ID, email, phone, and department. Let's assume employee ID, email, and phone are unique. Department is not unique. Step 1. Identify all attribute sets that uniquely identify a row. These are your superkeys. In this case, employee ID, email, phone, employee ID plus email. Also unique but contains extras, so redundant. Step 2. Eliminate superkeys with unnecessary attributes. You're left with only the minimal superkeys. These are your candidate keys: employee ID, email, and phone. Now, you can choose one to be the primary key. Let's say employee ID. The others, email and phone, become alternate keys. Let's summarize everything we've learned about keys. Superkey: any set of attributes that uniquely identifies a row, may include extras. Candidate key: a minimal superkey, no unnecessary attributes attached. Primary key: the chosen candidate key used as the table's unique identifier. And foreign key: a reference to another table's primary key to create relationships. Why are keys important? Because they enforce uniqueness and integrity, enable table relationships and joins, keep your data structured, clean, and reliable. Now, we enter one of the most abstract and most important areas of database design: functional dependencies and attribute closures. If you want to design clean, normalized databases, you must understand these ideas. So, what is a functional dependency, or FD? A functional dependency is a relationship between attributes in a table. We say X determines Y, written as X to Y, if whenever two rows have the same value for X, they must also have the same value for Y. This is the foundation of relational logic. Let's take a simple example. Suppose we have a student database and we say student ID to name. This means if we know that student ID, we can uniquely determine the student's name. But the reverse is not true. Multiple students might share the same name. So, name to student ID would not be valid. Thus, student ID functionally determines name. Why do functional dependencies matter? Because they help us detect and eliminate redundancy, structure our tables properly, and preserve data consistency. They also form the basis of normalization, the process of refining a database into efficient logical form. To work with FDs, we use a set of rules called Armstrong's axioms, a formal system of inference. These axioms help us derive new functional dependencies from existing ones. There are 3 core rules. 1. Reflexivity. If y is a subset of x, then x to y. Example, if you have employee ID and name, then you definitely have name. So, employee ID, name to name. Rule 2. Augmentation. If x to y, then xz to yz. Adding attributes to both sides doesn't violate the dependency. 3. Transitivity. If x to y and y to z, then x to z. Like dominoes, if A leads to B and B leads to C, then A, by definition, leads to C. These 3 rules are sound and complete, meaning all other inference rules can be derived from them. Now, let's learn how to compute attribute closure, a key step for identifying candidate keys. We have a relation with attributes A, B, C, and D, and the following functional dependencies, A to B, B to C, and A to D. Let's compute the closure of A, written as A plus, or closure of A. This means everything A can determine. Step 1. Start with A plus equals A. Step 2. Apply the functional dependencies. Since A determines B, we add B to the closure of A, which we call A plus. So now A plus equals the set containing A and B. Since B determines C and B is already in A plus, we can add C to the closure. Now A plus equals the set A, B, and C. Next, since A determines D and A is already in A plus, we add D as well. So A plus now equals the full set, A, B, C, and D. Since A plus contains all attributes, A is a candidate key. It uniquely determines the entire relation. A canonical cover is a simplified equivalent version of a functional dependency set, with no redundancy. Here's how to construct it. Step 1. Break down the right-hand side. Split multi-attribute dependencies. Here's the example. If we have A determines B and C, we split it into 2 separate dependencies, A determines B and A determines C. Step 2. Remove unnecessary attributes on the left-hand side. If both A determines C and AB determines C exist, then AB determines C is redundant. Remove it. Step 3. Remove redundant dependencies. If a dependency can be inferred from others, it's not needed. Test each and eliminate duplicates. The result? A minimal, logically equivalent set of functional dependencies. This makes your schema design cleaner and normalization easier to apply. Let's review the key points. Functional dependencies express how one attribute set determines another. Armstrong's axioms help derive new FDs from known ones. Attribute closure reveals what a set of attributes can fully determine, critical for finding candidate keys. Canonical cover removes redundancy from FD sets, making your design lean and clean. Now, we're jumping into one of the most valuable and important aspects of database design, normalization. Have you encountered issues with redundant data, update anomalies, or ambiguous dependencies? Normalization's the solution. Let's do it, step by step. What is normalization? Normalization is the process of structuring data in a database in order to avoid redundancy and enhance integrity. It involves dividing tables and expressing data according to functional dependencies. But why normalize? Because badly structured tables cause data anomalies, like the insertion anomaly, which you can't insert without including irrelevant information. An example being you can't insert a new course without an assigned professor. The update anomaly. Fixing one record fixes it everywhere, or risk inconsistency. The deletion anomaly. Deleting one piece of data accidentally deletes other useful information. Normalization cures all of this. Let's walk through the most important normal forms, from first normal form to Boyce-Codd normal form, using simple, intuitive examples. 1NF, the first normal form. To satisfy first normal form, all attributes must be atomic, no nested values or repeating groups. No multi-valued fields. For example, imagine a table with attributes student and courses. Suppose John is enrolled in math and physics. If both values appear in one cell under courses, that violates 1NF. It's not atomic. Break it into two separate rows, one with John Math and the other one with John Physics. Now each field contains a single indivisible value. The table is in 1NF. 2NF, second normal form. To be in second normal form, the table must already be in 1NF. There must be no partial dependencies. Every non-key attribute must depend on the whole primary key, not just part of it. Here's our example. A table with student ID, course ID, and student name. Here, the composite key is student ID and course ID. But student name only depends on student ID. That's a partial dependency. Your solution? Split the table into two, a student table with student ID and student name, and an enrollment table with student ID and course ID. Now, each non-key attribute depends on the full key. The table is in 2NF. 3NF, third normal form. To reach third normal form, the table must already be in 2NF. There should be no transitive dependencies. A non-key column shouldn't depend on another non-key column. Our example? A table with employee ID, department ID, and department name. Department name depends on department ID, which in turn depends on employee ID. That's a transitive dependency. Split the data into an employee table with employee ID and department ID, and a department table with department ID and department name. Now, all non-key columns depend only on the primary key. With this, we're in 3NF. BCNF, Boyce-Codd normal form. BCNF is a stricter version of 3NF. To satisfy BCNF, for every functional dependency, x dependent of y, x must be a superkey. Example, a table with course, instructor, and room. Suppose a course can have multiple instructors, but each room is assigned to only one instructor. So we have room-dependent instructor, but room is not a superkey. That violates BCNF. Your solution is to decompose the table into a room instructor table, room and instructor, and a course room table, which includes course and room. Now, every dependency has a superkey on the left side. We're in BCNF. Let's practice normalization with this table. Your attributes are employee ID, name, project, and project_location. Your functional dependencies, employee ID dependent name and project dependent on project location. Is it in 1NF? Yes, values are atomic. Is it in 2NF? Yes, no partial dependencies. Is it in 3NF? No, there's a transitive dependency. Employee ID is dependent on project, and project dependent on location. So employee ID gets dependency on location. Your solution to this? Decompose into an employee table, which includes employee ID, name, and project, and also a project table, project and project location. Now the schema satisfies 3NF. When we normalize, we split tables to reduce redundancy and enforce dependencies. But we must preserve two things. 1. Lossless join. You should be able to reconstruct the original table by joining the decomposed tables, without losing any data or creating false rows. 2. Dependency preservation. All functional dependencies from the original table should still hold across the decomposed tables, without needing to recombine them. It's not always easy to preserve both, but in ideal designs, we do. Let's wrap up with a quick review. Normalization eliminates redundancy and prevents update anomalies. We move step by step. From 1NF, which is our atomic values, to 2NF, remove partial dependencies, to 3NF, remove transitive dependencies, and finally, BCNF, ensure every determinant is a superkey. Good schema design also ensures lossless join and dependency preservation. Mastering these forms will make your database more efficient, consistent, and maintainable. Now let's examine the relational algebra, the mathematical foundation of SQL and arguably one of the most important query tools for relational databases. Relational algebra is mathematics for data, a set of operations you can do on tables in order to get the desired outcomes. Relational algebra has its own set of core operations that form the foundation of querying data. Let's go through them one by one. 1. Select. The select operation is represented by the Greek letter sigma. It returns rows from a table that satisfy a specific condition. For example, if we want to find all students from the CS department, we select those rows from the student table where the department equals CS. 2. Project. The project operation is represented by the Greek letter pi. It returns specific columns from a table. If we only want the name and age columns from the student table, we project those attributes and discard the rest. 3. Union. The union operation is represented by the U symbol. It combines two relations with the same schema and removes any duplicates. To get all CS and EE students, we can union the two sets, and duplicates are automatically removed. 4. Set difference. The set difference operation is represented by a minus sign. It returns rows that appear in one relation but not the other. For example, to get students who have not graduated, subtract the graduated students table from the all students table. 5. Cartesian product. Represented by a multiplication symbol, this operation returns all possible combinations of rows from two relations. If we pair each student with all courses, the result is a Cartesian product of the student and course tables. While not always useful on its own, this is the basis for joins. 6. Rename. The rename operation is represented by the Greek letter rho. It allows us to rename relations or attributes for clarity. For example, we can rename the student table to S and rename its attributes to SID and SName. The join operation, represented by the bow tie symbol, merges rows from two tables based on a condition. To combine student names with department names, we perform a join between the student and department tables on the department ID. Joins are the heart of relational databases. They bring normalized data back together. Let's walk through a real example step by step. Our goal? Find the names of students in the CS department. Our given tables? Student, which contains SID, name, and department ID. And department table, which contains department ID and department name. Step 1. Join student and department on department ID. This connects students to their departments. Step 2. Use selection to filter only those rows where department name equals CS. Step 3. Use projection to keep only the name column. The final result is a list of names of the CS students, stored in a table called result. You'll see the corresponding algebra expressions for each step on the right side of the screen. Okay, you got that handled? Let's do a more complex query. Here's our goal. List course names taken by students older than 20. We have 3 given tables. We have our student, which is SID, name, and age. We have an enrollment table, which contains SID and CID. And finally, we have the course table, which contains the CID and the course name. Step 1. Use selection to get students where age is greater than 20. Step 2. Join that result with enrollment on SID. This gets their course IDs. Step 3. Join that result with course on CID to get the course names. And step 4. Use projection to return just the course name column. Our final result is a list of course names taken by students over 20, held in a table named result. Each step has an algebra expression shown to the right for reference. Let's wrap up this section with the key takeaways. Relational algebra gives us a powerful mathematical way to query and manipulate data. Core operations include select, project, union, set difference, Cartesian product, rename, and join. With step-by-step queries, we can solve real-world problems in a logical, structured way. And here's the best part. Once you're comfortable with relational algebra, SQL will feel natural because SQL is built directly on these same principles. Now, we enter one of the most exciting parts, and honestly my favorite, of our DBMS crash course, SQL, or Structured Query Language. SQL is how we talk to relational databases, from creating tables and inserting data to querying and analyzing it. It gives us 4 main categories of commands: DDL, Data Definition Language, DML, Data Manipulation Language, DCL, Data Control Language, and TCL, Transaction Control Language. These are your tools for building, managing, and securing your data. Let's begin with the first 2, DDL and DML. DDL, Data Definition Language, is used to define the structure of your database. Create to create tables, alter to modify columns or data types, and drop to delete tables. DML, Data Manipulation Language, used to modify data inside those tables. Insert to add records, update to change values, and delete to remove records. These are your day-to-day tools for handling data. Now let's look at the other 2 categories. DCL, Data Control Language, is used to grant or revoke permissions. Here's an example. Grant select on student to employee. Gives read access to the employee role. And revoke insert on student from guest. Removes insert access from the guest user. And TCL, Transaction Control Language, used to ensure data integrity during multi-step operations. Commit, saves the changes permanently. Rollback, undoes changes if something goes wrong. For example, subtracting money from one account and adding it to another should only commit if both exceed. Otherwise, we roll back. Let's look at 3 core query components. Select, specifies the columns you want to retrieve. Where, filters the rows based on conditions. Inner join, combines rows from 2 tables where a match exists. Here's an example. You want to retrieve an employee's name, their department name, and salary. You perform a join on employee and department, using a where clause to filter salaries greater than $50,000. This query uses all three: select, where, and inner join. Let's add some powerful tools for data aggregation and sorting. Group by groups rows based on one or more columns. Having filters groups after aggregation, unlike where, which filters rows before. Order by sorts results. Use description for descending order. For example, to get the average salary per department, use group by department, then filter departments with averages over $60K using having. Let's break down the three extended types of joins. Left join returns all rows from the left table and matched rows from the right. Right join does the opposite: all rows from the right table and matched rows from the left. Full outer join returns all rows from both tables, matched or not. These joins are helpful when dealing with missing data or optional relationships. Sometimes we run a query inside another query. This is called a subquery. In checks if a value appears in a result set. Get names of students in the CS department by matching their department ID with a subquery that fetches CS IDs. Exists checks whether any record exists matching a condition. Here's the example. List students enrolled in course 101 by checking if a matching record exists in the enrollment table. Then we have aggregate functions. AVG is average. Count is total count. Max min is highest and lowest. And sum, which is totals. Here's an example. Get the average age, total number, highest marks, and total fees collected. Let's compare two types of subqueries: nested and correlated subqueries. In a nested subquery, it runs independently of the outer query. Here's an example. Get all employees in the HR department by selecting HR's department ID from the department table. And correlated subquery depends on the outer query row by row. An example, get employees whose salary is above the average in their own department. Nested equals static, and correlated equals dynamic per row. Let's apply our SQL skills to a mini project based on a university database. Your schema includes these tables: student, SID, name, department ID, and age. Course table, which includes CID, CNAME, and CRS. Enrollment table is SID, CID, and grade. And finally, the department table, department ID, and department name. Let's walk through three queries using this schema. Mini project query 1, average age per department. Here's our goal. Find the average age of students in each department. Step 1. Perform an inner join between student and department on department ID. Step 2. Use group by on department name. Step 3. Use AVG on age to calculate the average per group. Your output? Each department with the average age of its students. Mini project query 2. Students enrolled in more than 2 courses. Our goal? Find names of students with more than 2 enrollments. Step 1. Join student and enrollment on SID. Group by student.name. Step 3. Use having count star greater than 2 to filter the groups. And your output? Names of students who are enrolled in more than 2 courses. And mini project 3. Students with no enrollments. Our goal? Find students who have not enrolled in any course. Step 1. Get all SIDs from the enrollment table. 2. Use a subquery or not in clause to filter student records not present in that list. And our output? Names of students who don't appear in the enrollment table, i.e., 0 enrollments. Let's summarize what we've learned. SQL helps you create and modify tables, query, filter, and join data, analyze data using aggregate functions. There are 4 command categories. DDL defines the structure. DML manipulates the data. DCL control permissions, and TCL manage transactions. Here are the key tools that you need to master: select, join, group by, having, where, subqueries, and aggregate functions. You can practice all of this using real-world schemas like university, banking, or e-commerce to build your skill and confidence. Now for the second to last topic of our DBMS crash course, and quite possibly one of the most significant topics in database systems: transactions and concurrency control. Imagine a bank transfer or online purchase is left half-finished. Spooky, isn't it? That's why we have transactions and solid mechanisms to maintain consistency even when things go wrong. But what is a transaction? A transaction is a sequence of database operations which forms one logical unit of work. Here's an example. To transfer $500 from A to B includes deducting $500 from A's balance and adding $500 to B's balance. We do not wish for this to be just one step out of 2 to be successful. Either both should happen or none. That's the golden rule. Every reliable transaction follows the ACID or ACID properties, 4 key rules that guarantee safe and predictable behavior. A. Atomicity. All or nothing. The transaction must either fully complete or not at all. No half-done updates. C. Consistency. The database must remain in a valid state before and after the transaction. Rules, relationships, and constraints must all be preserved. I. Isolation. Transactions must not interfere with each other. Each one should execute as if it were alone in the system. D. Durability. Once committed, the transaction's changes are permanent, even in the event of a crash. Together, these make up the ACID model, the foundation of transactional integrity. Let's trace the life cycle of a transaction. It moves through these states. Active, it's currently executing. Partially committed, it's finished but not yet saved. Committed, it's saved permanently. Failed, something went wrong, and aborted. The system rolls it back to undo any changes. This flow ensures that a transaction is either fully completed or safely rolled back if errors occur. Running multiple transactions at the same time improves speed, but it can also introduce errors if not handled properly. Here are 3 common concurrency issues. A dirty read, reading uncommitted data from another transaction. T1 is still updating and T2 reads it, even though it might be rolled back later. Lost update. 2 transactions overwrite each other's updates. T1 updates a balance, then T2 updates it. T1's changes are lost. Phantom read. Rows appear or disappear within a transaction. T1 counts 5 employees. While it's running, T2 adds 1. T1 checks again. Now it sees 6. That's a phantom row. To avoid concurrency problems, we want concurrent transactions to behave as if they ran one after another. That's called serializability. There are 2 major types. Conflict serializability. If transactions can be reordered without changing the final outcome, they're conflict serializable. We then check for conflicting operations, like a write followed by a read on the same data. View serializability. More relaxed than conflict serializability. Focuses on what data is read and written, regardless of operation order. It's harder to verify, but allows more flexibility. To enforce serializability, we use a locking protocol called two-phase locking or TPL. It has 2 phases. 1. Growing phase. The transaction acquires all locks it needs, but can't release any yet. 2. Shrinking phase. Once it starts releasing locks, it can't acquire anymore. This prevents circular waits and avoids deadlocks, ensuring that transactions execute safely and in isolation. Let's wrap up this section with a quick review. Transactions protect data consistency in multiple user environments. ACID properties guarantee that transactions are safe and reliable. Concurrency issues like dirty reads and lost updates can corrupt data. Serializability ensures correctness, even under concurrency. 2PL is a locking protocol that helps maintain isolation and order. Whether you're preparing for exams or building real-world applications, you now understand how databases think, behave, and protect your data through transactions. Now to your final lesson of your DBMS crash course. A quick but intense recap of indexing and tree-based structures which speed up database queries by orders of magnitude. Why indexing? It would be torture to read a 1,000-page book without a table of contents, right? That's what querying a large table without an index would be like for your DBMS. Indexing is like a smart map. It enables the database to directly jump to the data of interest, instead of looking at every single row. We can categorize index types into 3 broad types. The primary index. It's built on a table's primary key. The data is physically arranged according to this key. Speedy and simple, like an alphabetically organized dictionary. Secondary index. It's built on non-key attributes. Picture it like bookmarks. Easy for fast retrieval, but the information isn't stored in the same order. Clustered index. In this case, the data rows are stored in the index order, only one for each table. It's like keeping books on a shelf by author name, as opposed to just having them on a list. Now, let's talk about the tree structures used by most database indexes. B-tree is a self-balancing tree, where keys and data can be stored at internal and leaf nodes. This is appropriate for quick lookups, may require more space due to mixed node content. B+ tree is a variation, where leaf nodes store only real data, and your internal nodes store keys only. The advantages are more economical range queries. The leaves are linked. Better space usage. Implemented in most contemporary databases. For a quick recap, indexing is for rapid access to data. Types of indexes are primary, secondary, and clustered. B-tree stores keys and data together. The B+ tree stores data only in the leaves for databases optimization. Congratulations! You've reached the end of the DBMS crash course. Now it's time for a rapid-fire recap. Your top 10 takeaways in under 3 minutes. Let's go. 1. Databases are structured, secure, and scalable, unlike messy manual file systems. 2. 1-tier to 3-tier architecture, plus the 3-schema model. That's abstraction done right. 3. Entities, attributes, and relationships. These model real-world data with precision. 4. Tables equals rows, which are tuples, plus columns, which are your attributes, enforced by the integrity rules. 5. Your keys: candidate, primary, super, and foreign. These form the backbone of relational logic. 6. Understand functional dependencies, closures, and simplify with canonical cover. 7. Normalize to eliminate anomalies. Keep your design clean and consistent. 8. Build logic with select, project, joins, and more. 9. Master, select, join, aggregates, and subqueries. These are precision tools for powerful querying. 10. Follow the ACID properties for safe transactions, and use the B+ trees to optimize performance at scale. Before you go, don't miss your extras. Download the DBMS cheat sheet. Practice with 50+ curated questions. Links are in the slides and video description. Got questions? Drop them in the comments. We're here to help. Share this crash course with your friends. Let's all level up together. Don't forget to subscribe and turn on notifications. More deep dive courses coming soon. You did it. You've completed the DBMS crash course. Solid foundation, sharp concepts, and the confidence to tackle real-world database challenges. This is where it begins. Now, go put this knowledge into action. Thanks for watching.